So solutions. So p plus q to the 7th power equals some number times p to the 0, q to the 7, plus some number times p to the 1, q to the 6, plus some number times p to the 2, q to the 5, plus some number times p to the 3, q to the 4, plus some number times p to the 4, q to the 3, plus some number times p to the 5, q to the 2, plus some number times p to the 6, q to the 1, plus some number times p to the 7, q to the 0. Now let's check to make sure our exponents of the variable p increase incrementally from 0 to 7. So we have 0, 1, 2, 3, 4, 5, 6, 7. That's good. Then for the q's, it should be 7, 6, 5, 4, 3, 2, 1, 0. That's good. And you can also check, although this check is redundant, I want to point it out to you. 0 plus 7 is 7. 1 plus 6 is 7. 2 plus 5 is 7. 3 plus 4 is 7. 4 plus 3 is 7. 5 plus 2 is 7. 6 plus 1 is 7. And 7 plus 0 is 7. So now I'm going to start Pascal's triangle from the beginning just to show you the pattern. 1, 1, 1, 1, 1. 1 plus 1 is 2. 1, 1, 3, 3. 1 plus 2 is 3. 2 plus 1 is 3. 1, 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Now we put 1s on the edges. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Put the 1s on the edges. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And now we have 1, 7, 21, 35, 35, 21, 7, and 1. And notice here that there is a 7 here and there is a 7 here. That means we've done. And notice also, as I mentioned in the parent video for which this homework video was taken, in the land of Pascal we start counting with n equals 0, not n equals 1. So that's n equals 0. This is n equals 1. This is n equals 2. This is n equals 3. N equals 4. N equals 5. N equals 6. And finally, as we need in this expansion, we have n equals 7. And that's why this is the row of Pascal's triangle that we will use for this particular binomial expansion. So now all we have to do is put in the coefficients. 1, 7, 21, 35. 1, 7, 21, 35. And 35, 21, 7, 1. 35, 21, 7, and 1. And this is our answer. And we are done with problem number 1. Now let's do the second problem. The second problem, we're going to start off with something very simple, and this might take us out of math in the fast lane, because the easiest way to do this is certainly not using Pascal's triangle. But the purpose of this video is to give you a little more insight and a little more depth into how this binomial expansion works. So if we're going to expand p plus q to the second using this method, we're going to have to use n equals 2. So p plus q to the second power using this method is still some number times p to the 0, q to the 2, plus some number times p to the 1, q to the 1, plus some number times p to the 2, q to the 0. And let's make sure our pattern is correct and that I haven't made a mistake. So the exponents of p should increase incrementally by 1, starting with 0. So we have 0, 1, 2, that's correct. And q should be the reverse order, 2, 1, 0, that's correct. And while it is redundant to do this final check, still 0 plus 2 needs to be equal to 2, and 1 plus 1 is in fact 2, and 2 plus 0 is in fact 2. And so we have made no mistakes here. So now let's put in the binomial coefficients. So we have 1, 2, 1. And this is actually our answer. So let's simplify this a little bit to see if we are on familiar ground. Recall that x to the 0, as long as x is not equal to 0, is equal to 1. And so this p to the 0 term is equal to 1. So this term in its entirety is actually q squared. Now, recall also that anything to the first power is unchanged. So this term here is actually 2pq. And this term here, since q to the 0 is equal to 1, this term here in its entirety is equal to p squared. So what we have here is we have just shown using this method that p plus q squared is equal to q squared plus 2pq plus p squared. And this should look very familiar to you, because hopefully if you're watching this video, you have already squared a binomial. But let's do a really quick multiplication. Let's go p plus q times p plus q and square this. Now this x represents multiplication, it doesn't represent a variable. And let's actually do this and see what we get. So q times q is q squared. Q times p is pq. Put the 0 down. P times q is pq. and p times p is p squared. Draw the line. Oh, I'm running out of space. Draw the line, and we have p squared plus 2pq plus q squared. Now notice, these two terms are equal, except the order is different, but addition is commutative, so the order doesn't matter. And so we've seen that using Pascal's triangle in the binomial expansion theorem is certainly a very long way to go if you simply want to square this binomial. But it is, in fact, correct and is completely consistent with the laws of mathematics. So we've done A. In fact, we finished A over here. And now let's look at something that's actually easier but could seem more complicated. So now let's look at part B, p plus q to the first power. Now this is equal to some number times p to the 0, q to the 1, plus some number times p to the 1, q to the 0. Now let's see if the pattern is consistent with the more complicated questions that we have done so far. So p has to increase incrementally from 0 to 1. So we have 0 and 1. That's good. And q has to decrease incrementally from 1 to 0. And we have 1, 0. That's good. And it's redundant to do this, but I always like to do this. Notice 0 plus 1 is equal to 1, and 1 plus 0 is equal to 1. And now let's go to the n equals 1 row of Pascal's triangle. Notice I didn't say the first row of Pascal's triangle, because the first row is actually n equals 0. But the n equals 1 row of Pascal's triangle is simply 1, 1. And let's put this in. 1, 1. And now notice that p to the 0 equals 1. And q to the 0 equals 1. So that tells us that p plus q to the 1 has to equal p plus q. And it does, only it's in reverse order here. Here it's equal to q to the 1, which is q, plus p. But of course, addition is commutative, so p plus q equals q plus p. And we've shown that even p plus q to the first power conforms with the binomial expansion theorem and Pascal's triangle. Now the last homework problem here, it's very easy, but its simplicity is sometimes confusing. And so I want to use yet another color. I'm going to use blue. So let's look at p plus q quantity to the 0. Now this should correspond to the n equals 0 row of Pascal's triangle, which is here. And there is a single number, the upper vertex, which is 1. And that makes perfect sense. At least it should. Because p plus q to the 0 power, anything to the 0 power, should be 1. And it is. See? It's the upper vertex of Pascal's triangle. So this worked out beautifully. This worked out beautifully. This worked out beautifully. Even these cases, which seem way too simple to ever require the use of the binomial expansion theorem with Pascal's triangle, are still consistent with the binomial expansion theorem and Pascal's triangle. However, the method of using Pascal's triangle and the binomial expansion theorem really shines when we have a higher order expansion. And that's very easy.
If you like this video, give us a thumbs up and subscribe to our channel.